Okay, so welcome to the first lecture on quantum mechanics 1. The previous lecture was quantum mechanics 1, lecture 0. So the course is quantum mechanics 1, also known as physics 303. Okay, and this is today's lecture 1. So in last lecture, we talked about class policy and roughly the content of the course and grading, grade distribution and stuff like that. Okay, I think somebody has their microphone on, so please, yeah. So are there any questions from previous class?
আমার একটা প্রশ্ন আছে।
Yes, Abdullah? Did you say something?
স্যার, আগের ক্লাসে এরকম একটা জিনিস দেখছিলাম যে অ্যাঙ্গুলার মোমেন্টাম এটা ডাইমেনশন হচ্ছে মানে প্ল্যাঙ্ক কনস্ট্যান্টের ডাইমেনশন হচ্ছে অ্যাঙ্গুলার মোমেন্টামের ডাইমেনশন, দুইটা একই।
Right, right.
তারপর তারপর আরো কিছু রাশি আছে যেমন মানে এনার্জি আর হচ্ছে টর্ক, এই দুইটা রাশির ডাইমেনশন একই। তো
Right.
মানে এই জিনিসটা মানে আমার কাছে একটু আনএক্সপেক্টেড লাগে, মানে যে দুইটা ভিন্ন রাশির ডাইমেনশন কিভাবে একই, মানে এটা কোনোভাবে কিভাবে চিন্তা করলে হচ্ছে মানে এটা আনএক্সপেক্টেড লাগবে।
এটা আনএক্সপেক্টেড মানে দিস ইজ দ্য ওয়ে থিংস আর, হ্যাঁ, মানে অ্যাঙ্গুলার মোমেন্টাম আর কি টর্ক বলতে আর কি বলতেছিল, প্ল্যাঙ্কস কনস্ট্যান্ট।
জি।
Right, I don't know if there's something deeper, but the fact that in quantum mechanics there's something called an intrinsic spin, and that has the same dimension as angular momentum, and it can come in various packets of h bar. Maybe that has something to do with it. I would not associate any deeper significance to that. The thing to note about the dimensional aspects of various quantities is that it is something that you should be mindful of. Because I've often seen that, suppose you're trying to figure out a calculation, you're doing a long calculation, and you know that the end of the calculation is going to be angular momentum, okay? But instead, you get something and you see that its dimension is energy, okay? Or its dimension is angular momentum squared. That means you've made some mistake somewhere. Okay, so that's one thing that's how dimensional analysis helps you. The other thing is that sometimes if you know the dimensions of the important quantities of a problem, you can guess the answers because, up to some, order 1 constants, because what you can do is that you can put those dimensional quantity in a unique way such that the result has the dimension of the answer that you're looking for. So therefore, even without solving the problem, you can say that, this is actually going to be the correct form of the answer. Now, there might be some pi to 8 or even 100 that you do not get from doing this hand-waving calculation, hand-waving argument. So my answer is that, be mindful of, always be mindful of dimensions of quantity, and use dimensional analysis, whenever whenever possible, okay? And in some sense, this is the difference between physicists and mathematicians. Mathematicians don't really care about dimensions most of the time. For them, numbers are something without dimensions. If you're really a very pure mathematician, like a number theorist, numbers are just this is pure thing. Whereas if you're a physicist, numbers usually have dimensions, and they have nothing, I would say, sacred about them. They change depending on what dimension you use. And in physics, numbers usually always, come with some caveat, such as, if I tell you that the, 15 point, or I don't know, 13 point, what is the age of the universe? Does everyone know? 13.7 billion years or something? I forget what this digit is.
So it's 13.8, I think.
Okay, 13.8. Okay, so if I say 13.8 and then a bunch of dimension and 2, 3, 4, suppose I do a calculation in which, this is the number of billions of years of the age of the universe. Suppose I say that, right? So, these trailing digits, they can come out of my calculation, but do they have any meaning? Do they have any significance? No. My data about astrophysics and cosmology is not that good. I can only probably say take 4 significant digits, okay? So, as physicists, we, when we have a number at hand, the meaning of the number depends on the context, okay? So so this is somewhat, along the lines of dimensional analysis, okay? Okay, I'm not sure if that answers your question. I don't think there's in general, anything deep about the coincidence that 2 quantities can have the same dimensions. But, depending on the quantities, there may be a link, okay? Okay, any more questions?
No, sir.
Okay. All right, anyone else? All right. So I want to spend a couple of lectures, maybe this lecture and the next lecture, talking about some historical aspects of quantum mechanics. Okay, so why do we need quantum mechanics? And not just quantum mechanics, quantum physics in general. And the short answer is that because classical mechanics is not good enough. Now, what is classical mechanics? So when we say classical mechanics, we mainly mean Newton's equations or Newton's law. There are several laws that are relevant here. Newton's laws of, say, mechanics, also Newton's law of, universal gravitation, right? But we can even go further Maxwell's equations which are the laws of electromagnetism, and then we can further go and talk about special relativity. That is also a classical law. Einstein's special relativity, as well as general relativity. So these are all things that we consider as classical mechanics. And they fail to describe, for example, properties of matter, or I should say properties, but anyway, properties of matter at very small scale. Typically, this is not a hard and fast thing. So for example, in the scale of an atom, so an atom is about what, 10 to the power minus 10 meters, right? Or say on the scale of a molecule is about 10 to say 100 times an atom. It can be even bigger, for example, macromolecules, proteins and stuff like that, for example. And at this scale, we know that particles interact via their electrostatic charges, right? So there's really, if we ignore the inner making of a nucleus, so if you just treat the nucleus as a particle and electrons as particles, then their interaction is essentially Coulombic interaction, right? Because they have a nucleus has positive charge, an electron has a negative charge, right? So, however, if you have a system, if you have a system of, say, charges, they cannot be in equilibrium. And by equilibrium, I mean some sort of stable equilibrium under their mutual electrostatic forces. Okay. So what does this mean? So you've all done some form of electrostatics or something, some charge.
Is that the statement of Earnshaw's theorem?
Yes, this is the theorem. So this Earnshaw's theorem, right? And we're not going to prove this theorem, but you can, if you have done some electrostatics, you probably have a little bit of intuition. For example, if I put, say, an electron here and say a proton here and say another proton here, and this distance is, say, d, and this distance is also d, then proton number 1 is going to put an attractive force on the electron in this direction, right? Proton number 2 will also put an attractive force in this direction. And when the two distances are equal, they will cancel each other out. But this is not a stable equilibrium, right? Because if we nudge the electron just a little bit, it's going to go either towards either of the proton. And of course, we have to ask the question, what is holding the proton in place? So if you have a set of, electrostatic charges, in some arrangement, you can show that there is no stable arrangement just under electrostatic charges where, things are not moving, none of the charges are moving, but they are in stable equilibrium. So this doesn't exist. So this means that electrostatics, classical electrostatics, by itself does not explain the stability of matter. Okay, so classical electrostatics does not explain the stability of matter. Okay, so the other option that we have is that those charges must be moving. So, we have some sort of atom, which is a very small object, say its size is 10 to the power minus 10 meter or something like this. And if these particles are, they are contained in this small space, and if they're moving, then they must be changing their direction quite frequently, right? So, if the particles, on the other hand, so we are now going beyond the realm of electrostatics into the realm of electrodynamics. So if the particles are moving in a small, confined space, then they must be changing their direction of motion quite frequently. Now, when something changes, when a particle changes its direction of motion, we call that acceleration. Okay? And when charged particles accelerate, we have electromagnetic radiation. So such a system must always be radiating, right? But radiation contains energy, and therefore, such systems must be continuously losing energy, and therefore, they will basically just collapse on itself. So either way, neither by electrostatics nor by electrodynamics, so the whole field is called electrodynamics, the classical electrodynamics fails to explain why matter is stable.
I have a question.
Yeah.
if you have just a proton and an electron and you release them, wouldn't they come together and attract each other and come to a stable equilibrium, or am I misunderstanding that?
Yeah, they won't. So basically, it's not like it's not like well, if you consider them as classical particles, no, they won't, because as you know, an electron is a negative charge, a proton is a positive charge, so they would just attract each other and just like collide with each other, right?
Yeah.
Yeah. So, but if you're thinking that, okay, maybe, you know, we are thinking it's an inverse square law, maybe they're going to do something like the planets, as the planets go around the sun, right? And it turns out that, yes, that can happen. So, you know, the proton can be at the center and the electron can go around it, right? Now, the thing is that the proton, of course, will also go around in a small circle, but, you know, we are going to ignore that because the proton is so much more massive than the electron. But the thing is that the electron in this orbit is always going to radiate. So it's going to radiate radiation, which is related to the frequency with which it goes around the proton. So it's going to give out radiation with frequency. Now, as it gives out radiation, what will happen is that the electron will lose energy, and the radius of its orbit is related to its kinetic energy. And therefore, what the electron will do is that it will actually, you know, its radius will actually decrease until it collapses into the proton, okay? So here you see that this is basically what's going to happen. So yeah, you know, so we know that the hydrogen atom is made out of a positive nucleus, a proton, and an electron. So according to classical electrodynamics, there is no reason for the hydrogen atom to be stable. And you can calculate what this energy is going to be. And it's, you know, it's going to, you know, it shouldn't be there, okay? So you might say, okay, why does this not happen, say, for the sun and the earth? The answer to that is it does happen. But the gravitational radiation, the energy that this system is losing in terms of gravitational waves is very, very, very tiny. Okay? Because the recent discovery of gravitational waves come from the rotation of two, you know, black holes, mostly black holes and sometimes neutron star, right? So we need something, two very, very massive objects for the loss of the radiation to be significant in terms of in gravity. And that's because gravity is so much weaker than electromagnetism. You see, the gravitational force between two subatomic particles is typically 10 to the power 40 times weaker than the electromagnetic force between them. Okay? All right, so our statement is that classical electrodynamics fails to explain why matter is stable. Okay? We need something beyond classical electrodynamics. Sorry.